Alright, so welcome to lecture 39. So, I have been talking about Landau theory in the last class, and we have come to a point where we said well, okay, so we can actually look at phase transitions by just looking at these phase transitions as transitions where as phenomena where we have an order parameter of the system. So, the system goes from an ordered phase to a disordered phase, and the orderliness or the disorderliness of the system can be measured through what is called a order parameter. And this order parameter can be polarization, this can be some structural factors, right. So, we saw the C axis parameter of a crystal can be your order parameter, right, especially if you are looking at structural phase transitions like a tetragonal to a cubic phase transition or a rhombohedral to cubic phase transition where structurally the materials are changing, then you can look at structural parameters like volume of a unit cell or the C axis parameter or something like that, right. So, you can define your order parameters, but this order parameter should sort of should reflect the inherent order. So, every phase transition, right. So, I imagine that my order parameter is going to 0 in the high temperature phase or the high symmetry phase, right. So, so I have to define an order parameter such that the order parameter actually goes to 0, or that is my understanding of what disordered phase is, right. So, which is the high temperature phase or a high symmetric phase. Okay. So, using that we said alright, so if I have one order parameter for the system, right, so for an dielectric system, or if I have two order parameters and I am looking at the coupling between these order parameters, that is enough. I can define a free energy potential which is called the Landau free energy potential, and based on this free energy of the system, so what I derived last time is okay, so either in case of polarization, so say where polarization is up or polarization is down, both these energies, free energy, should be equivalent. And so, we define this free energy to be some sort of an even function, and based on this definition we just solved a simple quadratic equation, right. So, dp by dt df by dp equal to 0, and this simple quadratic equation yielded us that the first of all the shape of the free energy functional is going to be either a single well or a double well potential depending on which temperature you are looking at. If it is double well, I am just going to so I am looking at a bistable state. This state is either stable in polarization up or polarization down, right, and then the polarization, we calculated the polarization, the equilibrium value of polarization, not any polarization, right. So, at equilibrium polarization is either up or either down, and this equilibrium value of polarization goes towards the high temperature phase as you keep on increasing the temperature, right. And when this is such a thing is happening, so we stopped here in the last class, when such a thing is happening, right, so where the equilibrium polarization has gone to 0, at that point we say that a phase transition has occurred, right. And this phase transition turns out to be what is called a second order phase transition. In the sense that so you always have a dou f by dou p, right, continuously changes, right. So, let me put it this way. So, where the polarization itself, not dou f by dou p, but polarization itself continuously changes to 0. There is no abrupt change, right. So, if I am looking at first order phase transitions, polarizations abruptly go to 0, right. This is polarization versus temperature. Whereas, if I am looking at second order phase transitions, polarizations go very continuously to 0, right. So, this is a second order phase transition. Polarization or any order parameter for that matter, this is a first order phase transition. And polarization itself is nothing but dou f by some free energy. This is not the Landau potential, of course. This is some sort of a Helmholtz free energy. It is the first derivative of Helmholtz free energy, let us say. So, that sort of a thing, right. So, first derivatives of Helmholtz free energy can also act up as order parameters, right. So, let us put it this way. are also can be good order parameters like polarization, right, strain and so on and so forth, and they go to 0 continuously in a second order phase transition. So, there is continuity in the first derivative of free energy in some sense, continuously in second order phase transition. Okay. Anyway, so now to determine it experimentally may be a bit difficult, right. So, whether I exactly have a first order phase transition or a second order phase transition, but let us not go into the minute details of that. So, in general, so I go back to my second order phase transitions and then I say that okay, so I have some sort of a Tc here, and this Tc is what is called Curie temperature, right, and near Tc, right. So, my polarization goes to 0 as square root of T, right. So, P or minus of square root T, sorry, minus T is a positive number, right. So, P goes to 0, right. So, in the ordered phase, P goes to 0 as T power half in the or minus T power half in the Landau model. From Landau theory, let us put it this way. Right. In general, so Landau theory is also what is called mean field theory. We will not go into details, is also called right. Let us not go into details of these mean field theories and non mean field theories. In general, depending on the model that you use to simulate your system, right. So, at a more microscopic level, P can go to 0 as minus T power what is called beta, right. So, beta does not need to be half, right. So, beta is half only if you are in the realms of what is called mean field theory, right. So, this I am just stating it as a fact, I am not going into details of this. If I have to go into details, I have to do a full course on statistical mechanics. So, that is not the purpose of this course. So, I will just mention this fact for completeness, and so in general these are all power laws, right. So, P goes to 0 as a power law, as minus T power beta, right. So, this is a power law sort of behavior. Right. Now, if it is a first order phase transition, now I have an issue, right. So, now when I am experimentally measuring P as a function of temperature, right. So, I am experimentally measuring okay, this value I measure, this value I measure, this value I measure here, I measure here, I measure here, and then I am so the next temperature so it is going down so abruptly that it is here, right. Now, I have only these data points, right. So, when I am experimentally measuring, right, then I ask you the question, is it first order or second order, right. Now, from here to here, right. So, I am okay. So, let me mention that as a star or something like that, right. I mentioned this as a star, this as a star. This is one data point, this is a second data point. All my phase transition has happened here. Now, my question is, did it go in this trajectory very continuously, or did it go so very discontinuously in this trajectory, right. So, that portion I do not understand, right. So, then you may say okay, do not do this sort of a measurement in this region where I just have two data points. I am going to measure this as a star, this as another star. So, the question is it going continuously from this star to this star, or is it going in path 2 which is discontinuously, right. So, this will be sorry, let me use another pen. So, is it going in this path? This will be a continuous transition, this will be a discontinuous transition. So, then you may say okay, coarse grain it and you measure temperatures at much finer points, right. Okay, so, I measure temperature, then I have the next you measure the polarization at much finer temperature difference, right. So, if the difference between these two temperatures is 0.1 Kelvin, you measure it at 0.01 Kelvin or you measure it at 0.001 Kelvin. in any case there is some data sampling that you do, temperature has a minimum temperature step, right. So, whatever be the temperature step, I will always find myself in the situation where the last two data points are either I am not sure if between the last two data points I have a continuous transition or a discontinuous transition in some sense, right. So, it is experimentally it is so these are the sort of issues that come when I have to see whether it is a second order phase transition or a first order phase transition, right. So, what I end up doing then is I actually do some fitting, right. So, I look at P versus T, right, and then so I can have I am drawing it very continuously like an analytical function, but I can have these sort of discrete data points, right. I am going to fit it, right. If I can fit it to some power law, if P can go as minus T power beta, right, then I call it a second order phase transition. That is the continuity I am looking for, right. But if I cannot fit P to T power minus beta, if it goes faster than T power minus beta, right, if it goes more steeper than T power minus beta, something like this. So, this is steeper than P power, it is more nonlinear, T power minus beta or minus T power minus beta, then I call it a first order phase transition. Then I say experimentally there is a discontinuity there. Okay, experimental discontinuity. There is a discontinuity in P only if P goes to 0 faster than or steeper than minus T power beta. It cannot be fit to a power law, no power law fitting, right. Okay. So, that is the detail essentially. So, when we are doing experiments we need to be very careful, especially in phase transitions. When you are claiming that your phase transition is first order or second order, you have to do very careful measurements, right. So, the data points that you take, so you have to make sure that your system stabilizes at that temperature, the fluctuations in experimentally your if your control system is not very good, you will have huge fluctuations in temperature, right. So, you do not want that fluctuations in temperature. If I am measuring 0.1 Kelvin, I need my fluctuations which are 2 orders of magnitude less than 0.1 Kelvin, right. So, these are the sort of things that I need to look for experimentally before I go ahead and claim that I have seen a second order phase transition, right, or I have seen a first order phase transition, right. So, one needs to do very careful measurements, right, and then so then also you have a problem, then also you have a doubt whether it is going to 0 continuously or whether it is going to 0 discontinuously. Experimentally there is nothing called discontinuous, right. So, everything is it follows some data, you can always fit some sort of a continuous curve, right. But what is meant by continuity, right. So, the theory says that if you can fit a power law, P goes as T power beta or minus T power beta, then that is a continuous phase transition. If it does not, if it goes steeper faster than that as an exponential or some sigmoidal whatever it is, but it is faster than T power minus beta, then I will call it a first order phase transition, right. So, it is not following the dynamics of a second order phase transition. Okay. So, that is how I be careful and I estimate whether I have a first order phase transition or a second order phase transition. Okay. All right. So, in any case, so that is a bit of a detour just to tell you that experimentally things are not as rosy as the theory that we are doing here. Okay. So, okay. So, now we have looked at P, right. So, P has an expression from Landau theory which is square root plus or minus square root of minus 2 A2 tilde T divided by 4 A4. Okay. So, this is the this is the P equilibrium rather. Okay. All right. So, now let us look at what susceptibility is. Okay. Now, okay. So, for susceptibility, how am I measuring susceptibility? I measure, so if I have a single well potential, this is F versus P, I measure susceptibility only at equilibrium. So, this is dou 2 F by dou okay. So, not the Landau potential, but susceptibility is typically I take the system away from equilibrium, that is what we said, right. So, thermodynamically we take the system away from equilibrium, we drop it down and then we see what is the restoring force for for the system to come back to equilibrium, right. So, that is what is going to tell me the susceptibility. So, I am going to do it at equilibrium, right. So, the values of susceptibility that I will take are at P equal to P equilibrium. So, chi of P equal to P equilibrium. So, this is where I measure susceptibility. Okay. Okay. So, with that understanding, what is susceptibility? I mean, how am I actually going to do that? So, okay. So, I have F again is equal to F naught, or I will just write it as F minus F naught, my Landau potential F minus F naught is equal to A2 tilde T P square plus A4 P per 4, right. However, I am going to apply a small amount of electric field to perturb the system away from equilibrium, and that electric field is E, and the energy that it adds to the system is minus EP. Okay. So, the minus EP term comes in here, right. So, this is how I need to estimate the susceptibility. Okay. So, now what is dou F by dou P? Dou F by dou P is 2 A2T P equilibrium, okay. So, P plus 4 A4 P cube minus E, right, and this at P equilibrium, and I said that we are just going to do this at P equilibrium, is this, right. All right. So, now we know the values of P equilibrium, okay. So, let us keep that in mind. Now, what is, I take the double derivative dou 2 F by dou P square again at P equilibrium, okay. And I am also going to tend T towards 0, that is I want to see what is the susceptibility near phase transition. I am actually going to show if at the phase transition things like susceptibility are going to enhance or not. That is the basic premise with which I started with, right. So, that would be equal to, if I just write it out, it is 2 A2T, the P here is gone, plus 12, sorry, this is the plus 12 A4 P square, P equilibrium square. Okay, and minus dou E by dou P, right. So, dou E by dou P at P equilibrium again, right. So, now what is dou E by dou P? Dou E by, and now here is the trick, right. So, this is in general dou 2 F by dou P square, right. Now, what is happening to dou 2 F by dou P square? Let's pay some attention to that, right. So, okay. So, dou F by dou P. So, when I am actually moving away from equilibrium, right. So, I have a double well potential which is like this. I keep changing this double well potential, right. So, F versus P, right. So, I keep changing this double well potential, it goes like this, it goes like this, it goes like this, it becomes very flat and then it changes to this, right. So, this is my T equal to 0 or T equal to Tc, right. At T equal to Tc, or when I am approaching T equal to Tc, you can see that so it is not just, so the dP by dt, right. So, if I look at dP by dF by dP, right, dF by dP here is negative, dF by dP here is also negative, dF by dP here, sorry, dF by dP is 0, sorry, I am just confusing you, I am sorry. So, if I look at the curvature, right, so here the curvature is negative, dou 2 F by dou P square, here the curvature is again negative, whereas here in the paraelectric phase or in the high temperature phase, dou 2 F by dou P square is actually positive, right. So, this is stable, this is unstable, correct. What happens when at this point, at my critical temperature or the Curie temperature, at the Curie temperature dou 2 F by dou P square is actually equal to 0, right. So, the curvature it's a 0 curve potential, 0 curvature potential, right. So, so it's infinitely flat in some sense, okay. So, so as a result so at Tc, as T goes to 0, right, as T goes to 0, I am going to say that dou 2 F by dou P square is equal to 0, right. So, that is what I am going to say, and so I am going to just calculate susceptibility as t goes to 0 and at p equal to p equilibrium, right. So, then this equation, which is equation 2, let us say equation 2 becomes 2a2 t is a small number going towards 0 plus 12a4 p equilibrium square minus is equal to dou E by dou p, right, because my dou 2 f by dou p square is very close to 0, okay. T as t goes to 0, and so this is at p equal to p equilibrium, okay. So, now this person here, this quantity on the left hand, on the right hand side, dou p by dou E is my susceptibility, right. So, at a given electric field or at a given polarization, and dou E by dou p hence should be inverse of susceptibility. I am just going to do a one dimensional problem where I am not going to consider, I am just going to simplify and not consider susceptibility as a tensor or whatever, right. So, ideally it is the beta which is the inverse tensor of susceptibility, but here I am just going to do a one dimensional problem and call this 1 by susceptibility, right. So, what I have here is 1 by susceptibility is equal to 2a2 t to tilde t plus 12a4 p equilibrium square. Now, what is p equilibrium? As I am approaching, so p equilibrium also approaches 0. I am in this limiting towards 0, right, but its real value is this thing, right. So, it is going towards 0 from the low temperature, right. So, the real value of p equilibrium is minus 2a2 t by 4a4. So, for t less than 0, this is minus 2a2 t by 4a4, this is the p equilibrium value, right, p equilibrium square, value of p equilibrium square. For t greater than 0, p equilibrium square is equal to 0, okay. So, now if I calculate what 1 by susceptibility is, right. So, 1 by susceptibility, okay. So, let me use it let me use this color. At t less than 0, 1 by susceptibility is nothing but 2a2 t plus 12a4 p equilibrium square is just times minus 2 by 4, minus 2 by 4 is just half a4 a2t, okay. So, I have a 6 here and this is a minus. So, that is equal to minus 4, a4 also goes, a2 tilde t, right. So, 1 by susceptibility is minus 4 a2 tilde t at t less than 0, and at t greater than 0 I am going to substitute p equilibrium square equal to 0. So, 1 by susceptibility is just 2 a2 tilde t, okay. So, the slopes are different. So, what happens at, so if I am just plotting susceptibility as a function of t at t equal to 0, right, 1 by susceptibility is equal to 0, right. So, because t equal to 0 in both cases, right, but t less than 0, 1 by susceptibility has a higher slope, it is decreasing, but it has a higher slope. This is 1 by susceptibility, I am plotting 1 by susceptibility, right. So, this is t less than 0, and t greater than 0 it has half the slope, but it is increasing, right. So, this is 2a2 tilde is the slope, here the slope is 4a2 tilde, right. So, this has double the slope, albeit negative, this is negative slope, right. This compared to t greater than 0, right. At t less than 0 I have double the slope compared to at t greater than 0, okay. All right, where did we see this, right. So, 1 by susceptibility goes as t, right, or in other words susceptibility goes as 1 by t, right, or susceptibility, so if I just write what t is, goes as 1 by t minus Tc, okay. I can give a constant here, right. So, I can say in whatever phase, right. So, in both phases that is the case. So, susceptibility goes as C by T minus Tc, right. What is C? C is nothing but the Curie constant, right, and susceptibility is equal to C by T minus Tc. Let us say this is in the high temperature phase, right. So, so let us do this in the high temperature phase. Susceptibility goes as T, actually we exactly know how it goes as, 1 you know 2A2T, right. So, 2A2T. So, here there will be a 2A2. So, the Curie constant is susceptibility is equal to. So, the Curie constant is just 1 by 2A2 tilde in the high temperature phase, in the high temperature when T is greater than Tc. Okay. So, what is this? This is nothing but the Curie-Weiss law, right, that you may have studied in other courses, where susceptibility goes as 1 over T. As you keep approaching temperature T equal to Tc, susceptibility also increase, susceptibility also goes to 0, but as 1 by T, sorry, goes to infinity, but as 1 by T. Okay. Now, at T less than Tc, susceptibility also has goes as 1 by C by 2 T minus Tc, right, minus C by 2, where this time I have my C is the same value essentially. Okay. So, if I am looking at, if I am just plotting susceptibility as a function of T minus Tc or T, right, it is for T less than Tc it goes to infinity slightly slower, and for T greater than Tc it drops down faster, right. So, I have this sort of a plot, right. So, susceptibility versus temperature now, right. So, T, right, is going to look something like this from my, just from my Landau theory. Okay. Ideally at T equal to Tc, the value of susceptibility equal to 0 or value of 1 by x, sorry, susceptibility is infinity, or the value of 1 by susceptibility is 0. This means that at T equal to Tc, I have infinite fluctuations of polarization. Right. So, this is how a second order phase transition is happening, right. So, how and so my susceptibility actually catches the fluctuation, right. So, if susceptibility is infinity, that means my fluctuations at a microscopic scale, if I go back to again the microscopic picture or the StatMech picture, my fluctuations actually go to infinity, right. So, there is so much fluctuation in the system that so the system is going everywhere, it is going berserk, right. So, at the phase transition, right, and this berserkness in the system where fluctuations are infinite is what is captured as susceptibility going to infinity, right. So, typically susceptibility is not infinity because there are always some losses that compensate for this infinite fluctuations. So, fluctuations cannot be infinite, fluctuations will always be finite, but susceptibility enhances, right. So, it is not infinite, but it is very large near phase transitions. Okay. So, this is a temperature dependent phase transition, and in a temperature dependent phase transition we have shown that susceptibility is quite large just using a Landau phenomenological theory, right. So, the fluctuations are super large, and so this phase transition is quite large. Okay. So, so with that so let me just quickly show you a video of so this is susceptibility, right. So, susceptibility means at the phase transition. So, this actually tells us some insights about the phase transition, right, a second order phase transition. So, at a second order phase transition, P goes to P versus T, right. So, P versus capital T, P goes to 0, P goes to 0 as Tc minus T per beta or Tc minus T per half, right. Okay. So, now this beta is called a critical exponent, right, it is an exponent here. So, this beta is called a critical exponent. Similarly, susceptibility, what happens to susceptibility, that is the derivative of polarization with respect to electric field. Susceptibility goes to infinity, right. So, this at Tc, right. So, chi goes as so 1 by T minus Tc in the high temperature phase. So, and in the low temperature phase it is minus 1 by T minus Tc, but in any case chi goes to infinity as T power minus gamma, right. So, it does not need to be 1 always, 1 is the Curie-Weiss law, right. So, here for example chi goes as T power minus 1, right, but this 1 is the mean field case, or 1 is the case of Landau theory, and 1 is the what even Curie-Weiss had calculated, but in general, right. So, if I am using some other model, it can go to infinity as T power minus gamma, right. So, these betas and gammas are what are called critical exponents, right, and wherever this Tc that I just showed in the second order phase transition is called a critical point, where there is a phase transition happening from of course, it is a low temperature to high temperature phase, but it is a a low symmetry phase to a high symmetry phase. Okay. So, this is what happens to polarization as a function of temperature, right. So, I have ideally I have two solutions for polarization if I am changing the temperature, and both these solutions go to 0 this way, right, and from here I just have one solution of polarization. Okay. So, this is sort of I am looking at a part of what is called phase diagram, I am looking at phase transition. So, this should be phase diagram of some sort of a ferroelectric material, right, or any material where order parameter is going to 0 with temperature, right. So, of a ferroelectric, let us say. With temperature. Okay. Now, you can also ask the question, what will happen to polarization, right. So, this is P versus T, right. So, P versus T goes somewhat like this, right. But so there is another variable, another hidden variable here, which is the electric field. I can also apply electric field and change the polarization, right. So, electric field can also change the polarization. So, how is electric field changing the polarization? If I am here at this temperature, right, and so I fix the temperature T1, right. So, this is T1, T2, T3, T4 and so on and so forth, right, and this is Tc, and this is Tc plus 1, Tc plus 2 and so on and so forth. Okay. So, initially I have it is a bistable system. So, the system can either exist in polarization down or polarization up. So, I have this hysteresis loop, right. So, where this is polarization and this is electric field at a given temperature, right. So, this is a T1, right. So, I have this is up state, this is the down state, right. So, in my Landau potential these are the this is the down state and this is the up state, right. So, Landau potential is F versus P, right. So, I am doing all sorts of possible combinations, right. In the Landau potential this is down, this is up. Now, I change the temperature. If I change the temperature in Landau potential, what happens? So, this thing keeps going closer and closer like this. So, if I then at another temperature, if I apply an electric field, my net polarization, my remnant polarization decreases. So, my remnant polarization decreases and my material looks somewhat like this, right. So, as I increase the temperature. So, the remnant polarization is decreasing, where this is at T2. At T3 my remnant polarization is something else, right. So, it is further reduced, right. So, this is at T3. At T4 my remnant polarization is what color can I use now? Okay, so my remnant polarization is further reduced, right. So, this is T4. And Tc and beyond Tc what happens is so my remnant, it just becomes a nice, so there is no remnant polarization at all, this just becomes a nice paraelectric material, right. So okay, so there can be still some non-linearity, that is okay, sorry. Okay, so let me redraw T4 again. This is T4, right, and then so it just becomes a paraelectric material beyond Tc, right. So that I am going to draw with the blue color. So this is greater than Tc, okay. So T4 is in black, right. So you have two different stimuli here, temperature is one stimulus and then electric field is the other stimulus. And what is changing with both temperature and electric field? The polarization is changing with electric field and temperature. Okay. This is so that is your entire phase map. Your entire phase map is you have to look at polarization versus temperature, polarization versus electric field. The third axis is electric field versus temperature, right, that also you can look at. So all these three things together will compose of the phase diagram of my ferroelectric material. Okay. This is similar to, for example, when I talk about phase diagrams, the easiest or the most important thing, phase diagram in so according to me is the phase diagram of water, right. So in water, right, so I have I have volume, I have temperature, I have pressure, right. So I can actually put all the three on three different axes, right. So this is the pressure axis, this is the temperature axis and this is the volume axis, right. You see that the water phase diagram is in this 3-dimensional space, it's sort of not trivial, it's a bit complicated phase diagram, right. So if you look at it, so we can slice it, we can take the slices that we want at a given volume, right. So or at a given so if I'm slicing this phase diagram along the pressure and the temperature axis, then how does that look like, right. So that phase diagram is here. So I have ice, I have water vapor, right, and I have they all coexist in what is called a triple point, right. There is something here called a critical point. So critical point tells me the transition between water and water vapor, right. So this is like this is like my polarization up is one phase, polarization down is another phase in the analogy of ferroelectrics, right. But if I am at lower temperatures, these are two different phases, right. So polarization up is a different phase and polarization down is a different phase. But as I keep on increasing the temperature, right, the polarization, the contrast between polarization up and down keeps on changing, right. So the Landau wells sort of start to merge and overlap, and at the critical point it does not matter, water is the same as water vapor. Similarly, polarization up or polarization down does not matter, you are anyway in the paraelectric phase, right. So beyond the critical point what I have is what is called a superfluid phase, right. So this is the analogy, right. So in a water phase diagram, right, so I have water vapor and water, these two phases are equivalent to me having a polarization up and a polarization down, right. Now in this case, right, so what is polarization? Polarization is being determined by the density of water, right. So instead of the order parameter here is the density, correct. So if I am doing analogy, one-to-one analogy, right, between water phase diagram and the phase diagram of a ferroelectric material, one-to-one analogy, phase diagram of water and the phase diagram of a ferroelectric material, right. So, I am going to say pressure or okay. So, the volume of water or the density of water is similar to my polarization, right. Okay. So, then temperature is of course temperature, and pressure I am going to write it as some script p, right. So, this is pressure will be similar to the electric field that I am applying, right. So, these are the analogies with the phase diagram of water, okay. And so I can look at the phase diagram in the PT axis, which means I can look at my phase diagram, the phase diagram of the ferroelectric or the magnet in the HT axis. In the HT axis, so I have a I have an order parameter that is going from so I have an order parameter which is non-zero in the here in this part of the HT phase diagram, and beyond this I have a phase transition, right. So, this is very simple because so in a ferroelectric my up and down polarizations are very symmetric, right, whereas in water, the water and water vapor are not very symmetric phases, their density. So, here if density is -1, here the density is not +1, right. So, here but in case of ferroelectric material, if polarization is +1, here the polarization is -1, right. So, that is why it looks very ordered, but this is the same line as this line here, right. So, that is what tells me where the critical point is, okay. I can similarly see it as for example T versus V, right. So, here they are looking at the volume versus temperature. Volume versus temperature follows this sort of a dome, right. Similarly, my magnetization or polarization versus temperature follows this sort of a dome, right, with magnetization going to 0 as T minus Tc power half, right. So, and so on and so forth, okay. And similarly so that is how you see the analogy between the phase diagram of water and phase diagram of these ferroelectric materials, okay. Now, here I have a couple of YouTube videos that so if time permits I will play today, but no, so today probably I am running out of time. So, maybe I will stop here, and so since the YouTube videos are here, it may be good for you to first watch in YouTube, right. So, before you come to the next class, watch what is the critical point of water and what happens at the critical point of water. There are these very nice experiments that people do in YouTube, this is at YouTube, right. So, essentially what I am doing is I am increasing the pressure, so I am increasing the pressure, and I am coming to this point where which is at 218 atmospheres of pressure and 374 degrees Celsius, I get to the critical point of water. 218 atmospheres of pressure is large. So, people show in YouTube the critical point of carbon dioxide, which is much more which is at much lesser pressures, right. So, see what happens at the critical point, so visually see what happens at the critical point, right. So, you will understand what these fluctuations are. So, we will start with that video in the next class, and then we will see, because at the critical point in a ferroelectric material or in a magnet I have polarization order parameter fluctuations, right. So, which are infinite. In water, right. So, the order parameter we said is density. So, at the critical point I have the density fluctuations, right. So, water goes from water phase to a water vapor phase through these density fluctuations at the critical point, right. So, we will look at this idea in the next class, and we will see how these density fluctuations look like, and what is it that means what does it mean that water or water vapor is going to the supercritical state, right. So, how does it look like, right. So, you can actually see this. If there are density fluctuations, you can see them with optical microscope experiments. That is what people have done. If you have already this reference, noted down this reference, you can see this on YouTube, otherwise we will see it together and try to understand this, okay. All right. So, I will see you again in the next class. Thank you very much.